Thru-hole technology, also spelled thru-hole, refers to the mounting scheme used for electronic components that involves the use of leads on the components that are inserted into holes drilled in printed circuit boards and soldered to pads on the opposite side, either by manual assembly or by the use of automated insertion mount machines. History. Thru-hole technology almost completely replaced earlier electronics assembly techniques such as point-to-point construction. From the second generation of computers in the 1950s until surface mount technology became popular in the late 1980s, every component on a typical PCB was a thru-hole component. PCBs initially had tracks printed on one side only, later both sides, then multi-layer boards were in use. Thru-holes became platted thru-holes in order for the components to make contact with the required conductive layers. Platted thru-holes are no longer required with SMT boards for making the component connections, but are still used for making interconnections between the layers, and in this role are more usually called vias. Axial versus radial leads. Components with wire leads are generally used on thru-hole boards. Axial leads protrude from each end of a typically cylindrical or elongated box-shaped component, on the geometrical axis of symmetry. Axial leaded components resemble wire jumpers in shape, and can be used to span short distances on a board, or even otherwise unsupported through an open space in point-to-point wiring. Axial components do not protrude much above the surface of a board, producing a low-profile or flat configuration when placed, lying down, or parallel to the board. Radial leads project more or less in parallel from the same surface or aspect of a component package, rather than from opposite ends of the package. Originally, radial leads were defined as more or less following a radius of a cylindrical component. Over time, this definition was generalized in contrast to axial leads, and took on its current form. When placed on a board, radial components stand up perpendicular, occupying a smaller footprint on sometimes scarce board real estate, making them useful in many high-density designs. The parallel leads projecting from a single mounting surface gives radial components an overall plug-in nature, facilitating their use in high-speed automated component insertion machines. When needed, an axial component can be effectively converted into a radial component by bending one of its leads into a U shape so that it ends up close to and parallel with the other lead. Extra insulation with heat shrink tubing may be used to prevent shorting out on nearby components. Conversely, a radial component can be pressed into service as an axial component by separating its leads as far as possible, and extending them into an overall length-spanning shape. These improvisations are often seen in breadboard or prototype construction, but are deprecated for mass production designs. This is because of difficulties in use with automated component placement machinery, and poorer reliability because of reduced vibration and mechanical shock resistance in the completed assembly. Characteristics. While thru-hole mounting provides strong mechanical bonds when compared to SMT techniques, the additional drilling required makes the boards more expensive to produce. They also limit the available routing area for signal traces on layers immediately below the top layer on multi-layer boards, since the holes must pass through all layers to the opposite side. To that end, thru-hole mounting techniques are now usually reserved for bulkier or heavier components such as electrolytic capacitors or semiconductors in larger packages such as the TO220 that require the additional mounting strength, or for components such as plug connectors or electromechanical relays that require great strength and support. Design engineers often prefer the larger thru-hole rather than surface mount parts when prototyping, because they can be easily used with breadboard sockets. However, high-speed or high-frequency designs may require SMT technology to minimize stray inductance and capacitance in wire leads. which would impair circuit function. Ultra-compact designs may also dictate SMT construction, even in the prototype phase of design.